Ladies and gentlemen, we're continuing chapter 4. Today we're going to talk about buffers. Chapter 4 is about acids and bases. So the question is, what is a buffer? A buffer is a situation that resists change in pH. What's involved in this situation? You need a weak acid and its conjugate base, and that's not even the whole deal. You need a weak acid and its conjugate base, and the conjugate base must also be weak. And we're saying, why are all these things important? This definition is very important. How does it resist change in pH? Well, because there's an acid present in your buffer, it will neutralize any bases that you add to the system or the situation. And if you neutralize a base, that means when you add a base to the system, the pH doesn't just go skyrocketing upwards like you normally get with base being added to water, right? You add base to water, the pH just skyrockets. You add base to a buffer, the pH goes up a almost inconsequential amount, very small. Why? Because there's something there to react with the base. What else is in your buffer? There's a base to react with acids that you add to the system. Okay? So instead of the acid doing what an acid normally does, which is precipitously drop pH, goes down very fast if you add acid to water. If you add it to a buffer, it goes down a very tiny amount. So buffers' roles are to maintain pH near a certain value. Do not give me this value because you don't know it, but you do know several values that can be used. For example, you can make a nice, what we call a perfect buffer by mixing acetic acid. I will remind you that's a carboxylic acid with a pKa of 5. If you mix acetic acid with its conjugate base, which is called acetate, and you have a 50-50 mixture of those two things, the pKa of the acid is 5. How do you know that's a weak acid? But just based on numbers. Just 5's above 0, it's weak. Okay, now what's the pKb of acetate, knowing the pKa of its conjugate acid is 5? 9, which is also weak. Acetate's a weak base. Both partners are weak in their role. The acid is weak as an acid. The base is weak as a base. The combination is therefore a buffer. The pH will be close to 5. Where'd that number come from? That particular combination is good for pH close to 5. Where'd that number come from? Sorry? Even parts to what? Why is it not 7? Why is it not 14? Why is it not 11? Why 5? What was 5, the number that I gave earlier? I reminded you it is a pK what? A of what? What functional group? Carboxylic acid. pH is always close to pKa for the acid in a buffer. pH is always close to pKa for the acid in a buffer. pH is always close to pKa for an acid in the buffer. So next time I ask you what's pH close to, and somebody says 7, I'm saying that is not what I said 3 times in a row on the video dated October 10, 2022. I will remind you, pH is always close to what? pKa. pKa of the acid in the buffer. If there's one thing you remember from today, it's that. pH is close to pKa for a buffer. Okay? And the equation governing it, which we'll never use, but we use it conceptually because it has a log in it. We can't do logs without a calculator. But the only equation that's relevant, and it's just a reorganization of the Ka constant. This is math that got me here. You just have to believe it's true. Log of A minus over HA. And I really don't, you don't need to memorize this, but I really think you should. And it's not hard. I want to predict the pH. It's always close to pKa. You knew that already, right? So that part of the equation you got covered. pH is exactly equal to pKa if the log of A minus over HA is 1. And I think Mr. Sroor was getting to this. He was starting to talk about when you have like equal amounts of an acid and a base. I'd like to point out that HA is the generic acid. A minus is the generic base. When you have equal amounts of them, guess what the ratio is here? 1. What's the log of 1? 0. Why is that called a perfect buffer? pH is exactly equal to pKa. That's the perfect buffer. You know pH is always close to pKa. I said it 3 times on October 10th, 2022. Okay? I think it was 4 when I was done. Yeah. Okay? What happens if you have a 10-to-1 ratio of base over acid? There will be no surprises here. Bases do what to pH? Raise, yeah. I'm in Dearborn. More than half your answers will be the word higher. Like higher the temperature, Dr. Whitaker. It's a cultural thing. Raise the temperature is what we. I try to help. Okay, I got no problem with it. It's very, very accurate. The French say shut the lights instead of turn them off. So you know, every culture's got its own thing. Anyway, TMI, yeah. The ratio was 10-to-1 of base to acid. What's the log of 10? 1. What's the pH? 1 higher than pKa, right? Still close to pKa, but 1 higher. Now, if you have a ratio of 1 to 100, 1 base for every 100 acid. Now, log of 1 over, did I say 100 instead of 10? Yeah. I googled, I'm sorry, I wanted 10. 1 over 10 is 1/10. 10 to the negative 1. That negative 1 is your answer, isn't it? The log of 10 to the negative 1 is negative 1. So pH still close to pKa, but are you surprised when you had more acid than base, the pH went a little down? Please tell me you weren't surprised by that. It went down by 1 when the ratio was 10-to-1. Acids lower pH, bases raise pH. Doesn't that help you memorize the equation? Once again, we're not using it, but you should have it conceptually in your mind. Base is on top. The only way to get that number to go up above pKa is to have a positive value in this log base over acid thing. To get a positive value, you need an answer greater than 1 in the parentheses, right? Yes, bases raise pH. Acids give you a fraction here, don't they, if there's more acid than base? What's happening? Log of a fraction is always negative, everybody. Math fact 101. pH is going down with acids. Math and chemistry fact you kind of knew. All right, so that was a 10-to-1 buffer, either in favor of the base where the pH was +1 on pKa, or when the acid was 10-to-1, pH was 1 below pKa. The limit of a buffer, you need to know. You can't have a buffer with ratios that are more than 100-to-1 either way. So if you have more than 100 times base to acid ratio, you don't have enough acid to have a buffer. If you have more than 100-to-1 acid to base ratio, you don't have enough base to have a buffer. Remember, the base is there to react with acids. If there's not enough of it, it just gets used up and your buffer's shot.
So 99-to-1 is fine, but 100-to-1 is not.
100-to-1 it's not a hard limit. It's a guideline cutoff. Good question. He was asking if it's like, is it exactly 100-to-1 ratio when you don't have a buffer versus you're on the way to not having a buffer when you get up near 100. That's the guideline. Okay, so keeping that in mind, what is the pH range for any particular buffer that's allowed? Remember, the log of 100 is 2. The log of 1 over 100 is -2. What's the pH range for any conjugate acid base pair you choose for your buffer? Don't talk to me about a number. Talk to me about that thing that buffers keep pH close to. pKa plus or minus what is a buffer? 100-to-1 log ratio is 2. That's the answer. So for a carboxylic acid with a pKa of 5, You can have buffers going from 3 to 7, 2 below, 2 above. If you want a buffer at pH equals 11, tell me your acid-base pair. Your best acid-base pair.
5, 9.
I need to know the name of the acid and the name of its base. And this one's not even organic, so I need the exact name. There's no variables here. You can't just say any amine and its conjugate base, or you can't do that, because there's an acid with a pKa of 11 that is a particular acid. Have we learned them yet? Right? No. She gave me the second best answer. She said a combination of ammonia and ammonium would be a great buffer for pH 10, because ammonium's pKa is 10. Okay? I wanted the one that's a little better. I'd need a 10-to-1 ratio to get that up to 11, a 10-to-1 ratio of the ammonia to the ammonium. That's not ideal buffer. It's still a good buffer, but I can do a better pH 11 buffer that's perfect. Bicarbonate has a pKa of 11. My lab students will tell you it's a little closer to 10.5, Dr. Whitaker, but that's okay. The pKa table has been rounded, even confesses on the table. To make your life easier to memorize the numbers have been rounded. So you use the 11 for bicarbonate. You say a mixture of bicarbonate. Best pH 11 buffer was the question. HCO3 minus, and what's its conjugate? Do I want its conjugate base or its conjugate acid? Carbonic acid would be a mixture that has a pH of 6. Best pH equals 6 buffer. I'm going to put down bicarbonate again and H2CO3. How do you answer this? Oh, geez, don't change they got to be a conjugate pair, people. Okay, which one of those two is the acid, and why did it move on me when I moved the screen? That's a good question.
The one on the right is
Yes, and what's the pKa of the acid? Carbonic acid 6. Okay, please don't pick the conjugate acid of this, because that's what the pKa is going to be for that pair. I know this has it's a base or an acid, guys. You got to pick the right one. So I need to be the acid because its pKa is 11. So what's the other partner? A buffer is a mixture of an acid and its conjugate base. This needs to be the acid. So what do I need now? CO3 2 minus. Now, when you need bicarbonate to be the base in the buffer, you pick this combination, because the acid is the one that dictates the pH of the buffer. Okay? Now, if I wanted pH equals, and there's no accident in this number, it's the most important number in acid-base chemistry, especially for mammalian species. Where'd that number come from? pH of the blood, also known as, let's do hangman. Might have not enough blanks, too many blanks, I don't even know. You have to know this number and this word that we have to come up with. You must know it for the rest of your career. This is not for my class, it's for every class. Everybody in this room claims to be interested in some career of health careers. Pretend you really take that seriously. This word is what? Don't pretend. Be. Okay, we're learning. It's good. I'll just go from the outside. It's a new kind of hangman. Physical's close. Oh, I don't have the Y in it. Yeah. Go with it. Go with it. I was only one. There was two lines off. It's supposed to be physiological. It's a fancy word too. You sound real smart saying it. Physiological. Yeah. I know we haven't done much of an activity here, but good discussion. When are you within healthy physiological pH? I need a range of two numbers, low end and high end. And somebody's going to tell me a number that's going to kill somebody. It just always happens.
Is it 7 point?
What's normal range for healthy physiological pH? Anything outside this, you will be ill. You won't be in this room. 7.2, you are in the hospital for acidosis treatment. 7.2 is too low. You are in trouble. You're getting closer, but you're still too low. 7.4 is the right number.
7.4 to 7.5?
No, you got to be a little below and a little above for the range, right?
3.5.
Yes.
Wow.
Good.
5.5.
Yeah, you're only allowed 0.05 variation on that. So healthy is 7.35 to 7.45. And I got a new screen by mistake. I don't know. This happens. I did it twice. Seriously? 7.35 to 7. I want to make it look real. To 7.45. Less than 7.35. Acidosis. You can look up the symptoms. Greater than 7.45. What's the word that means basic? Also a Hall of Fame Detroit Tiger. Wow. We're going back to the 60s and 50s here. Alkaline. That's the tiger, sorry. Alkaline. Alkalosis is the name of the disorder. You're too basic. Okay. All right. Why is it so important to have that pH range, and why is it so narrow? Did you say the magic word enzymes? Did somebody actually say the word enzymes? I love it. Okay, let's get into it right now. Enzymes are in a bigger, broader category of biological molecules, right? What is it? What's the big, broad category that they're part of? Say it again. Proteins. From this day forth, when you hear the word protein in your brain, you do a programming thing. When I hear protein, I think the word shape. What the shape is. Shape will give the function, correct. So yeah, proteins are all about shape. Well, there's certain chemical things that maintain shape. The most important one is pH. pH is a measure of which specific ion's concentration. Well, hydrogen ion in biology and in chemistry in general, if it's aqueous chemistry, that hydrogen ion is not by itself, it's associated with water, right? What do you call that one? H3O plus. It's got a name. Hydronium. Not unlike ammonium that has the plus charge, that's the yum, with an extra H on hydro, which is water. Ammonium has the plus charge with the extra H on the ammonia, right? So this yum ending is a more general thing than you probably know. It can be a cation. All right, so where did I leave off? Okay, we got hydronium ion concentration is pH, that's what pH is, okay? And if it's 7.4, you're healthy. So we got our mixture of an acid and base. It's bicarbonate and its conjugate partner, carbonic acid. You should be able to answer this simple question. In your blood, given that these are the two principal components maintaining pH in your blood, tell me which one there must be more of in your blood right now. Because the number of your blood pH is not 6. It's above 6, which means there's more what? Base or acid? Base. Which of these two is the base? The left. You know you need at least 10 to 1. At least 10 to 1 ratio. because 7 is above 6 by 1. If the ratio was 10 to 1, you'd still be thick, but at least your pH would be 7, right? It's a little higher, closer to 11 to 1, but you don't have to know that. Okay, doing a lot of talk today. There's going to be 2 activities. This one's going to be called the Introduction to Buffers. I never got to the main chemistry deal about why pH must be so narrow. Well, she said enzymes. We got to proteins. Shape is very important. What's the principal force? One of the principal forces that maintains a protein shape is hydrogen bonding. Both within the molecule, holding its shape, and the molecule with its aqueous environment, full of water, which loves to do what intermolecular force? Hydrogen bonding. So here's your scenario. You got your normal protein with its correct shape and a water molecule here. And it's hydrogen bonding here. Probably should go off the share screen. Here we go. We got our protein with its normal shape here. We've got a water molecule right next door. And it's hydrogen bonding right there. Now, there's a hydrogen ion that's extra that you added to the solution. You added an acid. And this, say it was an oxygen, hydrogen bonding with a hydrogen. Oxygen from the protein, hydrogen bonding with the hydrogen from water. And now it sees this proton getting close. Which do you think it's more interested in? The slightly positive hydrogen in water or the fully positive hydrogen in a proton? Yeah, you like fully positive more. So the water says, okay, well, I can't compete with this guy. It gets out of there. The hydrogen ion comes in there, takes its place. And this thing now has got a different hydrogen bond than it did before. It changed shape. Even worse, I got 2 parts of a protein here. 2 parts of a protein in this shape right here. See it?
Yeah.
They're hydrogen bonding there to maintain this shape. Now a proton says, I'm better at that than you guys. It gets in there, and this guy that used to be the H hydrogen bonding says, I'm not needed anymore, and it just leaves. And now your shape went from this to this. That's a change in shape. Guess what happened to your enzyme function? It's denatured causes what to the speed of which it facilitates chemical reaction? Slows it down. Changing the shape slows it down. You're slowing down your metabolism by having your pH out of whack, right? Yeah, that's not good. No. Certain metabolisms going at certain rates, and then all of a sudden you're cutting that one off. Everything gets out of whack. Okay, good discussion.
Professor, is that what people drink, like alkaline water?
The alkaline water will be done off screen.